The plates that held the bridge up had never been strong enough, not for a single day of the 40 years cars crossed them. On August 1st, 2007, at 6:05 in the evening, the I-35W Bridge over the Mississippi River in Minneapolis fell in 13 seconds. 13 spans, 111 people in the water, 13 dead. The nation watched the footage and asked how a bridge simply falls. Investigators would spend months searching for the answer, and then they found it not in the wreckage, but in a set of drawings made in 1967, before the first bolt was ever tightened. This is Failpoint. Tonight's report, the I-35W Mississippi River Bridge. In the early 1960s, Minneapolis needed a crossing that could carry Interstate 35W over the Mississippi. The contract went to Sverdrup and Parcel, a respected St. Louis engineering firm. The design they produced was a deck truss, a structure where the roadway sits on top of a triangulated steel framework rather than hanging beneath it. 14 parallel trusses, each one a series of steel members meeting at connection points called nodes. Those nodes were held together by flat steel plates, welded and bolted into place. Engineers called them gusset plates. Nobody would call them anything else for the next 40 years. A gusset plate is deceptively simple. Imagine two wooden sticks meeting at an angle. Alone, the joint is weak. Glue a flat patch of wood over the joint, and suddenly the connection holds. Steel gusset plates work the same way. They are the knuckles of a truss bridge. Every force that travels through every member arrives at a gusset and gets redistributed. Get the plate right, and the node is stronger than the members it joins. Get it wrong, and the node becomes the weakest point in the entire structure. Sverdrup and Parcel's engineer of record ran the calculations for every gusset on the bridge. Most were correct. Several were not. The specific plates that would eventually matter were at nodes U10 on the upper chord of the main truss. 4 connection points, 2 on each side of the bridge, where multiple heavy steel members converged at once. The original design called for plates half an inch thick. The National Transportation Safety Board would later calculate that those nodes required plates at least 1 inch thick to safely carry the bridge's design loads. The error was not subtle. It was not a rounding discrepancy. The plates were specified at exactly half the required capacity. The bridge opened to traffic in 1967. The error opened with it. Over the following 4 decades, the bridge carried an ever-increasing load. Traffic volumes grew. In 1977 and again in 1998, additional layers of concrete were added to the road surface, each pour adding permanent dead weight directly onto the truss. By 2007, the bridge's own structure weighed roughly 20% more than the original design assumed. And the gusset plates at U10, already undersized on day 1, were now carrying loads their designers never intended, every single hour of every single day. The plates were not failing visibly. They were deforming, slowly, microscopically, bowing outward under compression, a fraction of a millimeter at a time. The bridge was inspected regularly. The Federal Highway Administration rated it structurally deficient in 1990, a designation that sounds alarming but legally means only that some elements need monitoring or repair. It does not mean a bridge must close. Inspection reports from 2001, 2003, and 2005 noted cracking in the truss. They noted corrosion. One report flagged fatigue concerns near the upper chord. None identified the gusset plates as undersized. This was not negligence in the ordinary sense. The inspectors were looking at surfaces, at visible cracks. The calculation error lived inside the original design documents, and nobody went back to check the math. By the summer of 2007, the Minnesota Department of Transportation had scheduled a major resurfacing project for the bridge. Work began in late July. Crews set up in the center lanes, directly above the main truss spans. On the morning of August 1st, contractors loaded the construction staging area with their equipment and materials: aggregate bins, sand, gravel, a concrete mixer. By early afternoon, investigators would later determine, approximately 287 tons of construction material had been positioned on the bridge deck. concentrated within a 60-foot stretch, centered almost precisely above the U-10 nodes on the south span. The weakest points in the bridge, carrying more weight than they had ever been designed to hold. Here is the precise mechanism of what happened next, because it matters. A gusset plate under compression behaves like a thin ruler pressed end-to-end between two palms. Apply enough force and it does not simply crack, it buckles. It bows suddenly sideways, losing nearly all its load-carrying capacity in an instant. Engineers call it compression buckling. The half-inch plates at U-10 had been resisting this for 40 years, absorbing daily loads they were never designed for, their capacity slowly eroded by corrosion and the accumulated weight of two concrete overlays. The 287 tons of construction material that afternoon was not the cause of the failure. It was the final margin, the last weight that closed the gap between what the plates could bear and what they were being asked to carry. At 6:05 p.m., the U-10 gusset plates buckled. The node gave way in less than a second. With one connection point gone, the load it had been carrying transferred instantly to adjacent nodes. Nodes also served by undersized plates. They failed in cascade, each one collapsing the margin of the next. The center spans of the bridge dropped as a unit, rotating as they fell, striking the riverbed and the banks in pieces. 13 seconds from first failure to silence. 145 people were injured. 13 died. 62 vehicles went into the river. The investigation would take 14 months, but the answer, it turned out, had been sitting in a filing cabinet since 1967. The National Transportation Safety Board released its final report in November 2008. The probable cause: the original gusset plates at nodes U-10 were undersized due to an error in the design calculations. The additional load of the construction staging material on August 1st provided the conditions that triggered the failure. The NTSB also cited the Minnesota Department of Transportation for inadequate procedures for managing loads during construction. The placement of 287 tons above the critical nodes had not been reviewed against the bridge's structural capacity. Two separate failures, one in 1967, one in 2007. They had to arrive together for the bridge to fall. The collapse changed bridge inspection practice in the United States. The NTSB recommended that all fracture-critical bridges have their original design calculations independently reviewed, not just visually inspected. It also exposed a systemic gap. Inspection programs were built to find visible deterioration. They had no mechanism to catch a calculation error made before the first rivet was set. Hundreds of bridges across the country were subsequently re-examined for undersized gusset plates. Several were found. The I-35W was not an outlier hiding in plain sight. It was a proof of concept for a failure mode the inspection industry had not formally acknowledged existed. The replacement bridge, the St. Anthony Falls Bridge, opened on September 18, 2008, 13 months after the collapse. It was built with a redundant design, no single point of failure. The original I-35W bridge had stood for 40 years. It had been inspected dozens of times. Engineers walked its steel, photographed its joints, filed their reports. None of them were looking for an arithmetic error on a drawing made before some of them were born. The bridge was not pushed past its limit on August 1, 2007. It had been past its limit since the day it opened. Every failure has a point. Find it before it finds you.